So let's talk about parametric equations. So parametric equations, just like polar equations, are a different way to graph. They're a different coordinate system. So our rectangular and Cartesian coordinates, what we're used to graphing with, right? We have equations that are like y equals f of x. Our points are graphed as an x comma y, where x is the independent variable, y is the dependent variable. Versus parametric curves, where now there's actually 3 variables because there's one called a parameter. So instead of having one equation like we do over here, we now have 2 equations. And our points they're still x comma y points, but x and y are based on this parameter t. So x and y are both dependent variables now on a third variable, which is called the parameter t. We often use t simply because it's usually based on time. So parametric equations, because of this parameter, they don't always like start at a single point and go in like a normal direction. Like most of our curves, like in functions, go from left to right when we graph, but sometimes these can go from right to left. So the direction is based on how the parameter works with the 2 x and y equations. So parametric graphs, you'll often see little arrows on them for showing you the direction of the curve. Parametric equations are great for position, velocity, and acceleration questions since we can separate the horizontal and vertical components of movement. And if you take physics, these should be really familiar to you because of projectile motion and all of the equations that go along with that, where you can analyze both the horizontal and the vertical components independently of each other, right? These are also very similar to vectors, which you'll see with both x and y equations as well. So I'm really grouping this in with also covering vector equations because there's really nothing in parametric equations that we do in vectors that are different. Just a little bit of the vocabulary is different. So quick equation of some parametric equations. We're going to graph and show the direction of the parametric curves given by x of t is t squared minus 4 and y equals 2t. We're doing this without a calculator. So I'm going to quick draw myself a little xy coordinate plane. That was not great. Can we back that up? Okay. And I really don't think that y-axis is straight, so I'm going to try that again because that's going to bug me otherwise. Okay, maybe it is. Okay. Right, so instead of like a normal T-chart, like with a 2-column table to graph, we're going to use 3 columns. So we need t, x, and y. So if I let t be 0, I'm going to get negative 4 for x and 0 for y. So I'm going to graph 1, 2, 3, 4. So there's my starting point. Right, if I plug in 1, I get 1 minus 4 is negative 3 and y coordinate of 2, so negative 3 comma 2. Right, and then we'll just keep going. So then I'm going to get 0 and 4. Right, we'll graph a few more points. So 3, so 9 minus 4 is 5, and 6. So 1, 2, 3, 4, 5, 5, 6. And then I don't think I'm going to be able to fit much more in my graph. So this one is going like this, right? And our parameter starts here, and we're going in this direction. So sometimes you'll see those little arrow marks around the curve. We could also plug in negative values as well. So we could get the other part of this curve too. Right, if I plug in negative 1, I would get the same negative 3x, but now I would get negative 2 for y. Right, if I plug in negative 2, I'm going to get 0 and now negative 4. Right, if I plug in negative 3, I'll get same x coordinate of 5, but y coordinate of negative 6. Right, so but the important thing is like we don't draw like the arrow like this like we would on a parabola. It's still going like this. The curve is still moving in this direction. So if we were thinking about this in terms of the motion of like a particle, the particle is moving in that direction along the curve. So we can also sometimes convert between parametric and rectangular curves by doing something called eliminating the parameter. This one's pretty easy to see because we can kind of see what the graph makes the curve of in rectangular coordinates. So usually what we want to do is we're going to write our two equations. So we have x is t squared minus 4 and y equals 2 times t. So over here, this equation's a little easier to work with. This tells me that 1/2 of y is equal to t. So then I can go over here and say, well, x is then equal to t squared, which is 1/2 y, minus 4. So if I simplify that, I get that x is just equal to 1/4 of y squared minus 4. And that's a fine equation for a rectangular curve, right? It's an x in terms of y, but that's okay because otherwise if we solve for y, we have to do plus and minus square roots, so we can just leave it like this. So we've eliminated the parameter because now the equation is just in terms of x and y instead of any t's at all. So we got rid of the parameter in totality. Sometimes you can't do that because the curves are a little bit too complex to do, but sometimes you can, and you can turn them back into rectangular functions.